My name is Peter LaFosse. This is Rusty Wagner. We're from Vector 35. We're developers of Binary Ninja. This is Sophia D'Antoine. She's a researcher at Trail of Bits. And we're going to present about program analysis using Binary Ninja. So first, set the stage. The motivation behind this talk is, we're going to talk about the motivation behind this talk. Then we're going to go into the current state of program analysis, specifically concerning the various ILs that are available. Rusty's then going to talk to you about the design goals in what we saw in those and how we wanted our system to be different and better. And then Sophia's going to talk about actually writing tools built upon this analysis that help you to find bugs. So one of the big issues that a lot of reverse engineers get into is they tend to micro-focus down on the concrete assembly language instructions, and we feel like a lot of people can get wrapped around the axle with that. And instead, if they would be able to translate to a different, more symbolic form, then they would be able to reason over the actual underlying code more effectively and increase their speed and effectiveness at reverse engineering and vulnerability research. And we also wanted to make a lot of the program analysis things that people hear about, read about in papers, and make that more useful and accessible to the everyday reverse engineer. So to understand program analysis, you have to understand what the foundations of that are. And the foundation is having a semantic understanding of what code actually is done. Now, you could do this directly on the assembly language. You could model every single assembly language instruction, but that would be very difficult and tedious. So most people choose to translate that concrete instruction set to a intermediate form of some sort. So why would we do this? The biggest reason is it gives you an abstraction for your architecture, so you don't have to rewrite your analysis every single time on a new architecture. And another big reason is because these typically have a smaller number of instructions than something like x86, which has over 1,000 instructions. When designing an intermediate language, you have a few competing things. One of our primary goals was that the intermediate language be something that is easy to lift to. You can easily translate it from an x86 or ARM instruction to an intermediate instruction. Now that means a few things. Anyone that's done this will tell you how difficult flags calculations are. They're a pain in the butt. So if you're going to design a language, you should take flags into account. And you should also not try to translate too far. So you want to take the smallest step from a low-level concrete instruction to this intermediate form. You don't want to have to, say, do type recovery on a assembly language instruction. You leave that for later stages. Since Binary Ninja is a interactive tool, it's important that it be easy to read. Not just because Binary Ninja is interactive, but it also makes it easier to find bugs in your lifting if you can read the intermediate language easily. One of the things that enhances readability is using tree-based infix notation. This is more analogous to C. The thing on the left is assigned to the thing on the right. So EAX equals EBX plus 2. And you don't abstract registers, so you don't have 1 equals 2 plus, the constant 5. You also don't emit flags calculations except when it's necessary, and if you can avoid lots of temporaries that makes it more difficult to read because you have a lot more indirection. So a word about the size of the instruction set. If you have a very, very tiny instruction set in your intermediate language, that's very easy to analyze, but it's more difficult to lift to. So you have this balancing act when you're choosing every time you choose to add another instruction, you have to realize that's going to cause more analysis, but every time you decide not to add an instruction, you've got to realize that it's going to make it more difficult to translate from a assembly language to that intermediate language. So what are the available options today? There's a few: BAP, VEX, REAL, LLVM, and IDA maybe. So BAP, binary analysis platform, it has a tree-based structure, which is good. It does help readability a bit, but all their flags calculations are explicit. It's all written in OCaml, and nobody outside of academia wants to write in OCaml. And it looks like this. It's horrible to read. If you would prefer to read the thing on the right, then God help you. VEX is probably the single worst intermediate language that you could possibly choose for translating an assembly language from. All their registers have been converted over to numbers, so you have some mapping of number to native register. It's all single assignment. Assembly language is not single assignment, so you have multiple stages that you would have to run through for each assembly language instruction that you want to lift. There's over 1,000 instructions in VEX, and they say it's RISC lag, which maybe ARM RISC lag. Maybe they're comparing it to ARM, I guess. Even Anger, we talked to some of the guys from Anger, they're like, oh yeah, we're moving away from VEX. And they're pretty much the only ones that use VEX as a binary analysis platform. VEX is great for if you want to do emulation, and that's what it was meant for, but not for binary analysis. This is what a single instruction looks like. You'll notice that you actually have to physically assign the next instruction pointer there at the end. That's what that's doing. Real, this is, sorry Halvar if I say anything that offends you. Real has some good points, but the instruction set is 17 instructions. They're very proud of it only being 17 instructions, but if your whole goal is to get as little instructions as possible, you could just lift to brainfuck, and there's a lot less instructions there, and that would be better. But of course, you don't want minimal instruction set. Can't be the only goal here. It helps for some things, but it hurts for other things. If you want to have higher level of abstractions, it's nearly impossible to do with an instruction set with an incredibly minimal number of instructions. Also, flags are explicit. This is my favorite slide. This is one x86 instruction to the real equivalent. Yeah, that's pretty difficult to look at. So LLVM, it's a great tool. There's lots of things that are built upon LLVM, and it's a great end goal, but we feel like it doesn't make a great first stage goal. Everyone wants to be able to leverage the tools that LLVM has, but this is a compiler. We want a decompiler. We want things that go the opposite direction. Instead of coming from source to assembly, we're going the opposite direction. So we have different goals than LLVM does. So it's also incredibly difficult to lift to. expects instructions to have types, and as we said before, it's very difficult to lift an instruction when you also have to apply a type to it. Then you have to, you don't want to have to define at the point of lifting whether an instruction or a type is a pointer or an integer. You leave that for later stages. It's also SSA, assembly isn't, and usually they abstract the stack to a structure, which causes its own set of problems. And finally, IDA. Well, IDA really isn't a program analysis tool. There's rumors that they have an intermediate language, but there's no APIs for this. IDA's just is not a choice for program analysis, honestly. So if you're trying to use it as such, don't look elsewhere. Use any of the other things I said not to use. That'll be better than IDA. So Binary Ninja's answer to this is the Binary Ninja intermediate language, which Rusty is going to talk about.
Hi, I'm Rusty Wagner, and I'm the lead architect on Binary Ninja's IL, and I'm going to talk about our design choices. So why did we implement our own IL? Well, the popular existing ILs that we have, as you could see earlier, were not very human readable. We really want our IL to be human readable. We want it to actually be what reversers would go to instead of something that they just analyze on. We want it to be more readable than the assembly. Also, the existing ILs are single stage. What this means is there's exactly one representation of the IL. So it doesn't, basically with the existing ILs, it doesn't matter what kind of analysis you're trying to do. It's always in the same form. And sometimes that's not, like, sometimes they're doing low-level questions like stack analysis, and sometimes they're trying to answer more high-level things like, what is this mem copy here doing? So we want to do something with a multi-stage IL. Also, writing a lifter for new architectures tends to be pretty tedious and difficult in a lot of other ILs, and we want to create tools to make it much easier to lift. So the Binary Ninja IL is actually a family of multiple different kinds of ILs. At the lowest level, it's very close to what you would expect out of an assembly language, and then you proceed forward to higher level ILs, which would actually be much more like decompiled output at the end. Other goals that we have is that we definitely want it to be computer understandable, so we want to provide things like SSA form or 3-operand form, and allow you to compute based on that IL. That also requires us to make the IL plugin understandable, which means that plugins need to be able to interact with our IL. And we don't want to hide anything from you. If we do analysis on something, we want to provide that as an API so that you can write plugins based on it and analyze things. Again, we definitely want it to be easy to lift new architectures. And we also want to provide that avenue of being able to translate our IL to other ILs, for example, LLVM. Our IL reads a lot like pseudocode, so even in the lowest level form, it reads kind of like a bunch of C code. The flags we actually abstract and fold into readable human-like expressions. So here's an example of our IL. On the left, you see x86-64 assembly, and on the right, we have our low-level IL. You can see that it's near one-to-one mapping, so it's very easy to write a lifter that would output that. It's very easy to read, and at the bottom there, you can see we folded the compare and conditional jump into an if-like expression that's very easy to read. And this is another example of the IL. Here we have MIPS assembly on the left. Doesn't matter if you know how to read MIPS or not. On the right, you can pretty much guess what things are doing just based on the simple layout. So we have multiple IL forms, as I hinted out earlier. And if you're writing an algorithm to analyze the IL, you would want to you can pick the right IL for the job. If you're doing low-level IL or low-level type queries, like what does the stack pointer look like, you can do it on a lower level form. And here's the different ILs that we have. First, you start with lifted IL. This is what the architecture plugin would take from assembly and convert to IL. Then we resolve the flags usage of that assembly, and that becomes low-level IL, and that's what you saw on the previous slides. Then, of course, you have the SSA form of that if you need to answer data flow queries. And then we translate that to medium-level IL. Here, we actually resolve the stack usage, so stack variables become just regular variables at this point, and we also run type propagation at this stage. And then we would translate that into high-level IL, and this would be basically this would be very close to a decompiled output. So the medium-level IL is not actually out today, but it's coming very, very soon, probably in the next couple weeks. And high-level IL is a future goal. So every aspect of all of these ILs is accessible from the plugin API, and all the analysis that we do internally, we actually expose it as an API as a public API. In fact, our user interface in Binary Ninja is implemented as a plugin to the public API. There's absolutely nothing hidden in the API. So again, we want it to be easy to lift new architectures. So as Peter hinted at earlier, it's an expression tree. So basically, this allows you to write a modular lifter implementation. For example, in x86, an operand can be either a register or memory oftentimes. So you could write a function that says read operand, and you can just, at that point, decide, is it a register or is it memory? And you create an IL expression for that read from memory or register, and it returns the IL expression. Then you can use that in all of the instructions that could use that to easily build a modular approach. And we also created this thing called semantic flags, which greatly eases the burden of performing flags lifting on native architectures. So semantic flags is basically the architecture plugin defines a set of flags and what their semantic roles are. And for every instruction, you define what flags that writes or reads. And then we perform data flow analysis to actually link every flag, anytime you read a flag, to where that flag was written. And if it's an obvious semantic effect, we just fold it into a readable expression automatically. In most compiled code, this actually resolves pretty much every usage of flags completely automatically with no effort whatsoever from the architecture plugin. It just takes care of itself automatically. And if there are special cases, like you've got some weird code that's doing something out of the norm, it will fall back to concrete expressions, and you can express the flags explicitly. So here's an example of semantic flags in action. On the left, you have what we call the lifted IL. This is what the architecture plugin actually writes out as its output. And on the right is low-level IL with the if-style expressions that you saw earlier. So the star there on that subtraction instruction on the left, that means that that instruction writes to all the ALU flags. The architecture plugin would basically specify that that's the set that it writes to. And then in the if statement, you see this U greater than. That means that it's the flag condition representing unsigned greater than. So what Binary Ninja does is it sees that read there, the unsigned greater than flag state, tracks it back based on the flags that needs, and it finds the subtraction instruction. Well, if you're doing a comparison and the source is a subtraction instruction, that's just a simple comparison. So we fold it down into what you see on the right. So now that we have flags resolved, we have low-level IL. However, stack is still represented as just memory access. So the problem with that is you can't really do data flow on memory very easily. We need to translate it into a form that's easier to perform data flow on. So that's when we start to translate into medium-level IL. So the first thing we do is translate to SSA form. If you don't know what SSA form is, this is static single assignment form. Basically, it means that every variable is written to exactly once. If a variable is reused, you make a new copy of the variable. And if control flow basically merges two writes where it could be either value, you emit what's called a phi function, and that combines those control flow effects. So the nice thing about SSA form is that data flow is actually completely implicit. There's only one definition for every variable. And if it did come from multiple locations, you'll always have a phi function that says where those came from. So it's very easy to perform data flow on this form. So we actually use this form to do data flow on the stack pointer, to figure out where all the data variable or all the stack variables are. And this actually handles very nicely non-standard frame pointer variable. IDA has trouble with this. Like, I've seen binaries that use ECX as a frame pointer just because the compiler decided it wanted to, and it didn't work in IDA. But in our system, it just tracks it back to the stack pointer and handles it gracefully. So once we have our stack layout, we translate all the stores and loads on the stack to stack variables. So here's an example of our medium level IL. On the left is low level IL, and on the right is medium level IL. As you can see, the medium level IL is simpler and easier to read. Everything's a variable. It doesn't matter if it was a stack variable or a register. It's all just based on variables. You can resolve calls into something that's more readable. It's very, very easy to read at this point. And since registers and stack are actually treated both as variables now, you can actually track data flow between them. So no longer do you have to really care about that stack model anymore. You just deal with variables now. So if you translate to SSA form on this, you actually get implicit data flow on both register and stack variables, which is quite nice for doing analysis. So one thing you would want to do with this, and one thing that we do, is to do jump tables with it. So how would you implement jump tables? If you're IDA, you would have one of two methods. You would actually take all the compiler combinations and on all architectures and do basically pattern matching to find jump tables, or you would have architecture specific emulation, which is a lot of work. If you've ever tried to write an architecture plugin for IDA, it takes a long time. So we want to simplify this. And so we made a new algorithm for doing jump tables. So our jump table resolution is actually based completely on path-sensitive data flow. So during our SSA conversion process, we actually track the control flow dependence of every block. So we know what path the program had to take to get down to the jump instruction that we're querying. Our data flow computations allow disjoint sets, so you can have a disjoint range during your jump table computation if some weird compiler optimization decides to do that. The reads from memory are simulated so that we can actually simulate the table lookup that the jump table is going to do. And basically at the jump site, we just query this set of possible values from the data flow system, and that is your jump targets. And you just, at that point, you have your jump table resolved. So here's an example of us doing our jump table resolution. So down at the bottom, you see the jump x8 number 3. This is SSA form, so each assignment to the variable has a new copy. That's the third copy of x8. So we want to solve for that to find out what are the possible values of that register at that point so that we can find out where this jump is going to go. So first, we start tracing data flow backwards with SSA. Every SSA variable has exactly one definition, so it's pretty easy to follow it back. We end up at this x8 number 1 here, which is used in a computation for the address here. So we need to figure out what values this could have. So we trace it back to its definition. So this value here is used in a branch comparison. But this branch condition must be false to reach the jump site. That's where the path dependence comes into play. So we have an API that says, do we know which way this branch took? And in this case, it would say yes. We know it took the false branch. So since we know that's false, we know that this value is between 0 and 1f inclusive. It's guaranteed because we know that expression is false. So at that point, you have new information, and you can simply simulate forward at that point using that range, and everything will fall into place. You'll know how big that table is. You can keep track of all the values. When it adds to the set of possible values, you just simply do an addition on the set of possible values, and you will reach this jump with the addresses of all the different branches it can take. So more complex jump idioms may actually require multiple sources of information that you need to merge. It's actually pretty simple to do this with SSA. If you have an SSA fee function, you just compute the set union of all the different values it could have. And for a specific SSA variable, all you do is compute the set intersection of the definition and all uses of the information you know. If you don't know anything, you just consider it the set of all possible values, and your set intersection will narrow it based on the information that you know. So this single jump table algorithm can work on all architectures because it's done entirely on IL. So once you've lifted to IL, it just works everywhere. So jump tables work on current and future architectures with no effort at all from the architecture plugin. It just happens automatically. You don't have to do anything for jump tables. The control flow dependence information that's used for doing path sensitivity is also accessible from the API. Anyone can use that. And also, when you query for a set of possible values, for example, to find out where a jump is going, you can query that on any instruction or even any IL expression and find out what kind of possible values it has from the API. So medium level IL is quite nice. It actually has type information, stack knowledge, and SSA form. And that actually sounds a lot like LLVM. So we're actually going to use it to translate to LLVM in the future. And further analysis we can do to actually translate to high level IL. This is what we're going to build our decompiler on, because we definitely want to write a decompiler. It just takes time to get there. These are steps along the way to building a decompiler. And every aspect of this IL is completely accessible from plugins. So as we add things, you'll get new APIs accessible to you that you can perform heavier analysis, easier analysis, and all of that. So I'm going to hand it over to Sophia, who's actually used this for real work.
Cool. So we have this great IL now. We have tons of APIs that we can use to interact with this IL, query it for information. And we want to know how we can use it for profit. So how can we actually use this API? So some things that they didn't mention is Binary Ninja's API comes in the form of a headless API as well. So you can use it in the Binary Ninja GUI as well as just in your terminal using Python, C, or C++. Some things that I really liked about it is that it has a similar concept that LLVM-IR does, in the sense of functions, basic blocks, incoming and outgoing edges. The incoming is actually a little bit new because they needed it for dominators in dominant frontiers, so that just got added. You have the ability to get certain register states as Binary Ninja's analysis finds, and also some naive and not so naive range analysis now. So the new range analysis is actually quite robust. And that was actually quite interesting to me because me and a coworker were talking about maybe using Binary Ninja's API to rewrite a tool called Pagai, which is an awesome tool but written in OCaml, and it does range analysis. So hopefully that takes that project over. All right, so at first when I was just using the API, getting used to the headless API, I wanted to write a simple tool that looked through a program and looked for certain properties that I was looking for. So in this case, I wanted to know where my data, so my input data, got written to the stack. Pretty simple. You can go through the program, figure it out. Statically, and this is just an example of what bin bash looks like in Binary Ninja. I'm not able to pull up my demos right now just because they're on my computer, which was having issues. So these pictures will have to suffice. And this is what it looks like when you're using a different view of the IL. And it's a little bit more readable. So the script itself was quite easy to write. This is just using the Python headless API, so I could just run it in my terminal. And it works pretty simply. You give it a program, it loads it into its analysis engine, runs all of its analysis over it, builds up different trees, and you wait for that to finish. This is using the old API, so if you ran this right now in the updated binary Ninja API, you would actually use a different function here, and then these variables there are optional now. So going through it, I want to look for areas where my memory writes were based on mem copies. So you can kind of search or look through the program for different types of memory writes, and this was just an easy one that I could grab. So I'm looking for the memcopy function, so I got the address of that. And then I find different references to that function. So much like the LLVM uses, and you can iterate over those uses, I was iterating over the uses of the memcopy function. So I'm getting the function that it was referenced in, as well as the address, and that's just for personal use if I find something of interest and I want to go take a manual look at that in Binary Ninja. So going down here to find the different parameters that I was interested in, I just printed out the address, the destination and source of the data, as well as the length. And here I just did a simple grep to look for areas where I was writing to the stack. But you can have more robust checks of what you're looking for. So maybe you're looking for an area where the destination is a buffer or a memory area with pre-allocated space, and N is based on some sort of computation or user-affected input. So maybe you can look for certain buffer overflows there. So in the demo, I was going to run this and show the output, but if you find me later, I can show you that running in my terminal. So another awesome tool that we can write using the new SSA form, and this API is coming out in the next week or two, and this will be great. A lot of cool tools can be written off of this SSA API. But here I want to write a simple script which showed me areas where uninitialized variables were used in a program. This is very useful for vulnerability discovery and having the ability to quickly look through a very large program for areas of interest where these uninitialized variables are used is very handy. So here I'm just going through all the functions and all the basic blocks in those functions using the SSA form of those basic blocks. And for every instruction, I visit it. And I read the variable, read if the variable is written to, and I go look for different properties that I want to find. And in this case, I want to find uninitialized stack variables, but you can do other types as well. And I find the address of that. If not, then I continue. One thing to note is this script doesn't take into account five functions, so for loops, you would have a little bit of a problem with that. But overall, really quick, small script that you can write that gives you a lot of introspection into the program. So those two tools were very simple in looking for areas where certain properties existed in the program. So something more in-depth, more research-esque, you could say, that you could do with Binary Ninja's API is symbolic execution. So the benefits of symbolic execution is it's very accurate, tells you a lot about the program. However, it does take a lot of time and memory. And so it's often not feasible on real-world programs to do. So one idea, when I was trying to write a tool that uses an element of this, is to reason only about what I cared about. And I wanted to use an abstract domain to do this. So let's say I only cared about the types of my variables, the signs, the ranges, and look for certain bug types in those categories. I could use an abstract domain to analyze the program through the lens of types or through the lenses of signs. So I'm going to go quickly through this, but abstract interpretation, which abstract domain falls under, is basically the act of taking all of your concrete data and mapping that to a smaller set of abstract properties. So in this case, my sign or my type property would be in this abstract domain. And that mapping is called the Galois connection. So an example of what a compiler would do when it's trying to use abstract interpretation to to verify certain properties about a program is it knows that x's value is imprecise. However, it knows that it can apply a certain range to that type of x. So let's say x could only be 0 to 9. And it can go through this block of code and analyze it through the possible bounds of 0 and 9 and realize that when x equals 9, you actually get a right out of bounds for a. So no, this does require some small control flow analysis, but we do have that. So this is another example of using sign analysis specifically over this bit of code here. And applying that to the abstract domain of sign. So you take the variables a, b, and c and map those to your abstract values. So in this case, my sign domain is plus, minus, and 0, as well as question mark for cases where I just don't know anything about that. And this symbol down here, which means that it's a function pointer. And so I added that to my domain. So I wanted to create a sign analysis tool using the Binary Ninja API that analyzed the program through all of its variables through the lens of sign. So I could look for type confusion bugs. So for this tool, I wanted to under-approximate, and I want it to be path sensitive. So that means I wanted to take the CFG of maybe a function and take that and put it into different slices of a lattice is the structure I used, which each slice represented a potential path through that function. And each path, the variable may have a different sign than another path, or may have the same sign, but we don't know. And this just gives us a higher degree of certainty of where a potential bug might be. And for this tool, I ignored fractions. That's a side note. All right, so I wrote this tool, and it's great, and it's on GitHub. But the demo that I'm going to show, or was going to show, is on my other computer. But I ran this sign analysis over the PHP binary from last year. And this bug is patched right now, but basically it looked through all the variables in command file ex and determined that certain variables had a sign, and those variables which had a sign could be between the range of negative max, max allocation, to positive. However, they were being passed to a function which assumed that they were unsigned. So there was that change of type. They were being cast to unsigned. And so that area of change is where I thought, okay, that's probably an area where there's a potential bug might be there. And so it turned out there was a variable with a positive, negative sign, type, so signed, was being passed to a memcopy and being cast as unsigned. And going back up through the API, I could determine that that variable, which had a sign, could actually be negative. And we all know that when something's negative and cast as unsigned, it becomes very large. Another cool tool that you can do or make with Binary Ninja is a use after free analysis. So prior to this talk, one of my coworkers, Peter Goodman, wrote an awesome blog post and gave an awesome presentation about a tool called Points2, which is a use after free analysis tool. And there's several stages to finding use after free bugs. So for this tool, we had to convert binaries to LLVM bitcode or source code. But in this case, we already have the Binary Ninja IL. We already have that conversion. So stage 1 is done. Stage 2 is just to create that data flow graph. So we have to find areas where something is allocated, freed, and then used is the key. And so one difficult component to creating this data flow graph is to take into account callback functions, which are simple examples depicted here. And that's because using LLVMIL, it's actually slightly difficult to trace it back to functions which may affect that object's lifespan or lifetime, and then add that to the data flow graph. So for use after free analysis, it has to be context and path sensitive, and those two elements are key to writing a use after free tool. And the path sensitive API for Binary Ninja is there, and it will be released soon, I've been told, but if not, you can always implement that in the context sensitivity as well. All right, so another great tool that is actually written for Binary Ninja, and the blog post is down here, is devirtualization of C++ functions. Another coworker of mine wrote this one, and this is a useful script that's quite simple, and it takes, and it basically recurses back from areas where there's a call to a variable, and finds where that EAX, for instance, here is loaded, where that 4 is added to, and you can trace that back to the area where the address of the function that it's calling, and that's what it looks like recursively. And you can do all of this using that Binary Ninja API and write a script for it. So all these scripts and much more are released on the Trail of Bits GitHub. You can find the abstract domain plugin. You can find the C++ plugin for devirtualization. There's a depth first search path sensitivity tool that I started to write, and that's up there as well. However, that API might be released soon, so might not be needed. And then the memcopy example is up there as well, that I showed earlier. So in conclusion, Binary Ninja's website is a great resource, but also I loved this talk down here about abstract interpretation. I thought it was very clear and explained the topics very well, if you're new to it. And the only static program analysis book I've ever seen before is linked to right here. And I got my idea and a lot of the theory behind my sign analysis tool from this PDF. So it's a great resource, and it's actually a fairly easy read compared to a lot of academic things I've read. So in conclusion, Binary Ninja is great. And you too can be a Binary Ninja Rockstar, as it says down here. But it's very useful for writing really great tools that help you quickly introspect into a program and get a lot of information from the program, and looking for different things in it, or just exploring symbolic execution. So in conclusion, you can contact us at any of these emails or Slacks or even IRC, if people use that still. The Slack might have taken over, I don't know. Yeah, and that's our talk.
Stick it on for any questions. Okay, so who is the brave soul who has a question about abstract analysis? Is it Halvar? Excellent. Hold on. I will run a microphone to you, and I will give you your fully licensed copy. Let's hear some sparks.
Thank you.
Testing.
First off, great presentation. Secondly, fairly technical question on the lifting to the medium level IL. When you have a function that calls multiple virtual methods, or multiple virtual functions, and it's std call and frame pointer omitted, you need to know the state of ESP after the first virtual method call, but you can't know it because you don't know how much the calling side will have corrected the stack. Does the translator bail out and yell at you to annotate, or what do you do if you run a situation where the state of the stack pointer can't be determined, but you need to know it in order to know what local variables are being accessed?
Yeah, that's actually a big problem with Windows binaries in particular, where you don't know what the stack adjustment of a function is. So we do not have a solution for that yet, but we do know that IDA uses a solution where it basically knows that the stack should be consistent and then does algebraic solving to figure out what the constraints should be, and we'll probably implement a similar method in the future.
Yeah, they use simplex for it, but you get screwed if you have multiple calls in one basic block, one in a row, because it tries to resolve this constraint optimization thing there, and doesn't have enough information to actually tell you whether anything between the different calls will... well, either way, long story short, you will have to bail to the user at that point, I think, because I don't think there's an automated... Well, if you come up with one, tell me.
I'm going to go to the back of the room, because the back tends to get ignored.
Great talk. Thank you very much. I appreciate all the work that the Binary Ninja and the Trail of Bits people have been doing. Great tools. Minus the fact of calling out OCaml, because Coq you can extract OCaml code from Coq, and Coq's pretty badass. But I won't hold that against you. So the question about the chaining of plugins, or I have a question about the plugins, and as you mentioned in LLVM, there are passes, and then you can change passes, or chain passes, and have a pass manager that'll deal with dependencies. And the reason I ask for that is because once you start analyzing large code, you might want to start doing pruning on that graph. And so I didn't know if the plugins both support pruning of the graph, or as well as chaining of plugins. I have another question after that.
So we don't yet have anything for passes yet. We are definitely planning an analysis pass plugin so that you can actually create passes and chain plugins together like that. That is very much in the plan. It does not exist yet.
Cool. Such as work in progress. Another question is about memory usage. Would you say that within and I don't know if this code is open source or not, I forget, that you're fairly lazy or aggressive in terms of allocating memory as you expand out the graph?
We like to use the RAM that you have on your system because we like to make things fast. We're very multi-threaded, and we're pretty RAM heavy right now. We're trying to bring it down a little bit, but we think RAM is meant to be used.
Unlike IDA, we only have 64-bit code, so you can use more than 2 gig of RAM when you're analyzing a binary.
Hey, a few simple questions. First, what is the size of the binaries you analyzed so far? Second question is, what was the signal-noise ratio on the type analysis that you've made? And third question is harder, so we'll stop there.
I heard the first question was, what's the size? We've analyzed Chrome debug build, which is kind of pretty much the top end of what you would expect. It's like 1.5 gigs.
So like PHP, SSH, Apache, those things goes fine.
I mean, I read my sign tool over like JavaScript core and stuff too, so.
Okay, and second question was...
We routinely test on Unreal Engine 4, which is about 2 million lines of code, so that is a routine test case for us.
Good. And what was the signal-noise ratio on your type analysis? Like, did you find this PHP bug you mentioned you found? Like, have you found like 200 false positives together with that, or it was just the one hit you found?
There's definitely false positives, and that's because, I mean, a lot of the time, my analysis was a bit more high level. Like, I didn't have tons of filters for finding points of interest. I was looking for maybe one type or one class of thing that happened, and I was looking for that. I mean, to reduce the results, you would just, increase the number of filters that you put inside that analysis tool.
Got it. And last thing, have you considered using annotations to enhance your analysis?
Can you repeat that?
Have you considered using annotations to enhance your analysis? Like
Annotations.
annotating the
I've used
program, yeah.
annotations a lot for LLVM-based tools that I've written, but I haven't yet done annotations with the Binary Ninja IL.
Thank you.
I have also read the Moeller's paper on dynamic analysis, static analysis. So, does the tool work with dynamic web content which gets generated on the fly? Did you try generating call graphs for dynamic content, or control flow graphs for dynamic content?
Oh no,
Okay.
I did that.
Yeah, we're a pure static tool right now, but you can load a memory dump and then disassemble that. That's about the only way you can look at dynamic content.
Okay. Well, thank you so much. That was great.